Graphing circles using parametric equations. So take a look at this equation. Hopefully you remember it from an algebra class. It is the equation of a circle in the xy plane. The center of the circle is 0, 0. And the radius of the circle is given by that number on the right side. Specifically, that number is the radius squared, which means to figure out the radius, I would have to take the square root of that number. Square root of 4, of course, is 2. This becomes pretty simple to draw. If I'm centered at 0, 0, and my radius is 2, just start there, go out 2 in every direction. And so I'd have a point here, 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 and here. Do your best to make it look like a circle. And I've got my graph. Now, what if I wanted to recreate that on the graphing calculator, on the TI-84? It is possible to do that using the normal equation here. I would have to do some algebra. I'd have to get the y by itself. That's going to involve using square roots, the plus or minus. I'd end up having to use a couple of lines in the graphing calculator to graph this circle. But there's an easier way, and that is to use parametric equations. In fact, I am going to claim that this set of parametric equations will generate that same circle. X equals 2 cosine t, y equals 2 sine t, with t carrying on values between 0 and 2 pi. Let me show you that, in fact, this is the case, and then we'll talk about why it works. So on the calculator, we'll need to check our mode for a couple of reasons. I need to make sure I'm in radian mode if we're letting t go from 0 to 2 pi, and I am. I also need to make sure I'm in parametric mode if I'm not there already. So I think all my modes are correct. Then I go to the y equals area, clear out anything that was there before, and in their place, put in our new equations. X equals 2 cosine t, and then y equals 2 sine t. And then the window area is important. I'm going from t equals 0 to t equals 2 pi. That was the request. And then let's set the t step to something small just to make sure I can see enough points. I'm going to set it to be 0.1. Let's see, for the x and y values, we know this is supposed to be a circle with radius 2 in every direction, so going from -3 to 3 seems reasonable for both x and y. And then we'll hit graph. Now, you may be looking at that thinking, well, that doesn't really look like a circle. It looks too squished. That's just because the calculator screen is in the shape of a rectangle. You can see that it goes out 2 on the left and right, and also 2 up and down. So I know it's that same circle. What you can do to adjust for that rectangular screen is in the zoom feature, if you choose Z square, choice 5, then the computer will recalculate the window a little bit, the x and y values, so as to make your picture look more like what you would expect. And so here's that same circle that we drew on the paper. Notice if I hit trace, it starts me at the spot where t equals 0. Apparently, if you plug 0 in for t in the two equations, you get x equals 2 and y equals 0. If I arrow around, remember I told it to count by t equals 0.1, so you can see it moving through those values. And what has happened every time is this value for t is being plugged into these two equations, generating the ordered pairs that make up the circle. Now, let's try to answer the question, why did these two equations generate this circle? How is it that that's the case? I can answer that question by converting the parametric equations to the standard rectangular form. In order to do that, I'll need to eliminate the t in these equations and end up with something that only links up x and y. How will I do that here? It doesn't really look like t is very easy to get by itself, and that is true. Well, I can use a little trick. Watch what happens if I square both sides of these two equations. I will end up, of course, with x squared equals, let's see, 2 squared would be 4, and cosine squared would be cosine squared t. And cosine t squared would be cosine squared t. Similarly, in the other equation, I'll end up with y squared, and then 4 sine squared t. What I'm going to do now is I'm going to add these two equations together. So I'll add the left sides together and I'll add the right sides together. And that will give me x squared plus y squared on the left equals 4 cosine squared t plus 4 sine squared t on the right. Now so far, maybe you're thinking, are you sure we're getting anywhere? We still have these t's all over the place. Maybe you can see what's going to happen. On the right side here, if I just factor out the 4, then I'm left with cosine squared t plus sine squared t. And we know from the Pythagorean identity that that's just equal to 1. 4 times 1 is just 4, and so look what I've ended up with. X squared plus y squared equals 4, which was our original equation that we graphed up at the top. And so we've proven that these two parametric equations generate that same circle. Okay, let's answer a couple of follow-up questions. What if I just wanted to graph the left side of the circle, just the left half, in the graphing calculator? How could I make that happen? Well, let's look back at the picture. Remember, t equals 0 generated this point right here, and then as we traced through, we saw that as t got larger, we started moving through the circle in this counterclockwise direction. Well, I need to figure out what t value corresponds to this point right here. You can probably guess what it is. If I trace around, let's see, t equals 1.4. 1.5 is not quite there. 1.6 is a little too far, so something between 1.5 and 1.6. We can do better than that, though. I mean, look at the equations. I want to be at a y value of 2. So what t would I stick in here that makes this come out to be a 2? It would have to be 2 times 1 would make 2. Well, we know that if you put pi over 2 in the sine function, you get 1. Just picture the unit circle. Pi over 2 is between 1.5 and 1.6. Again, it's not surprising. T equals 0 landed us here. It makes sense that pi over 2 would land us here. I'm thinking that means pi here and 3 pi over 2 there. So if I want to adjust my picture, instead of counting from 0 to 2 pi, if I instead told the calculator, no, just show me t values from pi over 2, which will be the top of the circle, down to 3 pi over 2, then that should give me the left side of the circle just like we wanted. Let's take a look. And sure enough, there it is. The calculator is now only showing us those values of t. Okay, what about the second question? Let's say t stands for time. Let's say time in seconds. How can I adjust the equations so that one full rotation around the circle takes 2 seconds? Now let's see, how long does it take now? Well, we've just figured out that t equals pi over 2 lands you here, and then pi, 3 pi over 2, 2 pi would bring you all the way around. That's why we were using 0 to 2 pi, because that was plenty. If we go past 2 pi, we'll just go around the circle again. So right now, it takes 2 pi seconds to go all the way around the circle. 2 pi is around 6.28. I want one rotation to just take 2 seconds. Well, let's look at our equations here. Why is it currently taking 2 pi to go all the way around? Well, obviously because that's the period of the sine and cosine functions, right? After 2 pi, you're just going to start repeating those same values. What I need to do is I need to adjust those two equations so that instead of the period being 2 pi, like it is right now, the period comes out to be 2. Well, we learned earlier in the course how to do that. I just have to adjust my b value, my coefficient of the t. Remember we had this little formula, b equals 2 pi divided by p. In this case, the p, the period that I desire, is 2, and so when I plug that in, I get a b value of pi. So all I have to do to make this work out is adjust my two parametric equations so that the b value, the coefficient of that t, instead of being 1 like it was originally, it's now pi. So I'll have 2 cosine pi t, and y equals 2 sine pi t. I believe this set of equations should draw the same circle, but now make it so that it takes 2 seconds to go all the way around. So I'll try it out on the calculator. I'll go to my equations. I'll clear out what's in there now and replace the equations with what we just discovered. 2 cosine pi t for x, and then 2 sine pi t for the y. And I guess for my values of t, I should start at 0, and then I think it should just take 2 seconds to go all the way around. Well, let's hit graph and find out. There's the graph. I'm not sure we're convinced yet. Maybe if I hit trace, if I start tracing around, you can see, notice I'm already about halfway around the circle there. Aha, 1 second for t took me halfway around. Well, obviously then the other second, by the time I get to 2 seconds, I will have gone all the way around. Obviously, we could make similar adjustments if we wanted to either move slower or faster around that circle. Thanks for watching.